time in my life here. Last time was a year ago when it was the Kolmogorov Fest. So I'm sorry for being late. It's not that easy to get here. So I chosen the subject, which is a bit strange because it's a very old subject, and I did it more than 15 years ago, maybe, with Roslym. But as far as I was told that the seminar is mainly for physicists, then I thought that probably it would be more interesting than my more recent research. Okay, so I will speak about polar homology. And it's a joint work with Alexey Roslym, who is present here. I think it's my first time I'm giving a talk on this in your presence.
Second.
You also second?
There was a school in Switzerland.
Yes, you're right. Yes. But it was a lecture course. Okay, so let me start with some motivations. First motivation comes from very classical mathematics. So let X be a compact Riemannian surface. And suppose we are given a collection of complex numbers associated to each point, such that almost all of them vanish, which means that we are given a divisor. You can say it like that. A divisor, so this is a finite sum, where ai are complex numbers and xi are points on x. And recall that given a differential of third kind, which means given a, in other words, logarithmic one form, so let omega be logarithmic one form, or differential of third kind, which means that it has only first order poles. It's a homomorphic differential on x that has only first order poles. Then we can form the residue of omega, which is the sum over all points over x of residue of x at x times x. And since it has only finite many poles, this is also a finite sum, so it's a guy of that sort. And an actual question to ask is, what are the conditions on a divisor to be a residue of a one form? It's a classical so-called Cousin problem, and absolutely classical complex analysis. It is well known that simple proposition is that if let's call it D, if D is a residue of some omega, then there is a necessary condition that the degree of D, which is just sum of coefficients, must vanish. Well, it's a standard fact about residues, one of standard ways to calculate integrals, and so on. And the theorem is that the converse is true as well. It's a classical theorem by Cousin, I think. What does it motivate? It motivates a similar question in high dimensions. So what can one say in high dimensions given high-dimensional complex variety and some subvarieties on it, or maybe algebraic variety over C, or maybe over no other field. So given a variety and some collection of subvarieties and forms on them, when can one represent it as a residue of some other collections of subvarieties and forms? This is what talk will be about. Okay. Now, a totally different motivation for this thing. So the second motivation, it was 1, now 1, 2, comes from Черна-Саймонsa theory. Well, Черna-Sаймонsa theory is a big theory. I will speak about only a tiny part of it. Okay. Черна-Sаймонsa theory, again, I'm not pretending that I will describe all of it, just a very small piece of it. So let n be a smooth real now times compact and oriented, so with chosen orientation threefold. Then once we choose an orientation, we can integrate top forms on it. So let denoted by A1M the space of so-called fields, and in terms of geometry, it's just smooth one forms. On M. Then, as far as I understand, mathematical physical theory depends on which function on it are we considering. So it defines as an action functional and so on. So let's consider the following action functional. So let's send A by some functional S to S of A, which by definition is the most natural thing you can cook up out of one form and a threefold. You can just weight it with this exterior differential and integrate over M. This is a scalar, so it's a, we can say that it's a quadratic function on the space of all one forms, and in a sense it is positively defined. So one can say the distribution, it's a functional integral will appear, but of course I will not explain the rigorous way to do it. So distribution which sends A to e to the minus s of A. Okay? And now it's kind of distribution over space of all fields, of all one forms, and then if we are given some functionals, other functionals on one forms, we can consider correlations, mathematical expectation of these functions, mean value, and so on. So let's consider other functions which are more related to geometry. So each curve on C, on M, definitely defines as a functional on the space of one forms just by integrating, but not the curve, but curve with orientation. Actually. So let's consider a curve with orientation. Now, given C on M curve, oriented curve, also curve, we can consider the functional, linear functional on the space of forms, namely A goes to the integral over C of A. Right? And now, given two curves on the threefold, we can consider the correlation between those two functions. Why not? With respect to this distribution, of course, the answer depends on the distribution. And so let's define the correlator as integral over C1 of A times integral over C2 of A. So by definition is the integral over all forms with respect to some right weight. So e to the minus s of A, and the integral of C1A times integral of C2A. So as my course explained me, this is one should consider it as an infinite dimensional Gaussian integral, right? So it converges, everything is good in a sense. Well, anyway, it defines us some number.
Is it a correlation between
yes.
integrals or between the curves?
It's, I don't know how to answer. Correlator. Anyway.
It all depends on the positions of curves.
Defined by two curves. And so a theory by Witten is that if both classes of both curves vanish in the first homology of M, that is, we can consider some surfaces with orientation such that our curves are boundaries of these surfaces. Yes? So suppose it holds, then this number, so it is some invariant of two curves in a threefold, which are both homologically trivial. And of course, if you are from topology, you already guessed, if you didn't knew it, that it is just an even number of these two numbers, which is the intersection number of C1 with the surface C2, like that, where C2 is some surface such that the boundary of C2 is S2 is C2. Yes.
In fact, this version of what you call Witten's theorem was discovered by Polyakov long before Witten, but the contribution of Witten that he extended this to non-abelian.
Okay. Yes. Yeah. Let's think. Okay. So now the question is, does there exist, or what is the holomorphic analog of this? So here the question was about high-dimensional analog. Here the question was about holomorphic analog. And so now a third motivation, which somehow explains how to understand both of these, is some dictionary, and as far as I understand, it should be called Arnold dictionary, no?
Sorry?
The third motivation is some dictionary that probably should be called Arnold dictionary.
It is motivated by certain ideas of Arnold, but is not inside. For Arnold, it would be probably too simple.
We can put them quotes.
А предыдущее утверждение, оно имеет какой-то логический смысл? Действительно, можно меру какую-то определить, например, ну что корреляция правильно.
В этом случае это
то есть действительно можно...
не в этом случае...
Ну, Шенгауз это интеграл, это можно посчитать, как бы там все вычислить. Да?
Да.
Ну, там вычислить можно, определить.
Определить-то можно, что вычисляют?
Определить трудно, вычислить можно. Вино есть этикетка, да? Okay, let's go. So, the dictionary, I find it fantastic, and it was explained to me by my dear co-author. So, the dictionary is between smooth, real manifold, as above, yeah. And here, let's consider smooth complex, and I will say even algebraic property, because the theorem that I will speak about lives in the algebraic property. So smooth complex algebraic array. And the main part of the dictionary is that D should correspond to D bar. And out of this, you deduce all the rest. So for example, the round complex, D is above the round complex. So the round complex denoted by A dot M should correspond to Darboux complex. Which is given by A 0.0 ohms, okay, which has only DC bar, does not have DC. Then, well, D allows us to define, well, we consider cohomology of this complex. In particular, the first cohomology that appears are constant or locally constant functions. So locally constant functions, which are kernel of D functions, correspond to what? To holomorphic functions. Then, what are locally constant functions? Out of locally constant functions, you construct local systems. So, given a local system, local system, L, so you have some charts, and then you have functions, translation functions in the intersection of charts given by locally constant functions. This gives you a local system, or which is the same representation of I1, locally constant shift if you want. So that will correspond to just holomorphic vector bundle. Or if you algebraic complex, just algebraic vector bundle on X. Okay, then another thing is, an important thing here was orientation to get an integral out of a form. You don't have integral when you didn't choose the orientation, plus or minus 1, but it's still important. Sometimes there are non-orientable varieties, but locally at least you can speak about orientations. Okay? So what should orientation correspond to? And the orientation corresponds to top holomorphic form. And orientation is a section of orientation shift. Sometimes it is not constant, right? If your variety is not orientable, then you have the locally constant shift, which is shift of orientations. This is plus minus 1 local system. Yeah? It's rank 1 local system, and so it corresponds to what? To canonical class. And of course, if you think about perpendicularities, you get all this, of course. Perpendicularity. Okay, then now here we were speaking about cycles and oriented cycles, and we were integrating forms against oriented cycles. So what should correspond to oriented cycle, to an oriented cycle, or oriented chain? So oriented chain cycle is some let's say simplex with orientation, or some subvariety with orientation. It should be dropped. So it should correspond a pair which consists of a subvariety Z and some form alpha, where Z is some maybe reducible for simplicity subvariety, and alpha is top form. But you see, so here orientation is on something that doesn't have border. So if you want your cycles to have border, it is important to speak about all these things. You want to do something with orientation. Your orientation is broken on the border. So your form should be also broken on kind of a border here, and it should be a pole of your form. So here boundary of a circle should correspond, so I will write it below, but here I should put logarithmic top form. Logarithmic top form, and maybe I should remind what are logarithmic top forms, because this will be one of the main heroes further. So let me remind what are logarithmic top forms, and then I will continue the analogy there.
So you do not assume that your variety is Calabi-Yau?
Not at all. Absolutely not. Of course, it's a good example. It's an example when it doesn't have boundary, but probably it does. Okay, and because further we will also consider something with value in a vector bundle, and that means that allows your variety to be not Calabi-Yau, but still to have some non-trivial top form with value in some vector space. Okay, so let me briefly remind about logarithmic forms. So definition, suppose you have some variety V, abstract of the notations, and you have some divisor that is codimension 1 subvariety W. And so what does it mean that alpha is logarithmic along W? So assume for simplicity that all of them are smooth, complex. So what does it mean that alpha is logarithmic along W? It means that locally you can represent it as dt over t, I will explain, where it's beta plus gamma, where locally, so all this happens locally along t, along divisor, where locally along the W, so W is given as t equals 0, so it is the local equation of W, and beta gamma are regular, that is, do not have poles regular along W. So you have your V, you have W, and at each neighborhood you can represent your form like that, where T is a local equation of your subvariety, and then you weight it by two. You weight it by regular form of degree less by 1, and here the same form of the same degree but regular one. Okay. Some questions so far? Okay, and what is important about these log forms is that one has a well-defined residue of, let's note like that, VW of alpha from V to W, which is just beta restricted to W. Okay? It is well defined. It is a well-defined top form on W. You do the same in one-dimensional complex analysis when you have a point on a complex plane and you take a rate. Okay, I continue the dictionary then here. So here is the residue of alpha from Z to some B, where B is some divisor of Z. Okay, then what? Then here we do have, let's consider the dictionary. So here, a fundamental thing relating forms and cycles is the Stokes theory. Which tells us that the integral over the cycle of the differential of the form is the same as the integral of over its boundary of the form itself. Well, let's translate it here. What does it mean? It would mean that the integral of over z. So how do, yeah, I didn't say it. So here we can pair, we can integrate forms with cycles. How do we do it on the right hand side? If you have some form, which is 0p form, and we have some cycle with top still p form, golomorphной p form, we can just restrict our 0p form to the cycle, wedge it with the given orientation, golomorphной 1, and then integrate against the cycle. So here what we do is alpha, but I should take here the differential of a, so I take d bar a, and here what I should get is the integral over d of residue of d to alpha, because this is my boundary. Yes, so my differential, the boundary of d alpha is d residue to d of alpha, where d is a, maybe I should have put here d, where d is a divisor of poles of alpha. For simplicity, we assume for now that everything is smooth, okay? Because then I will define all of this, the complex of all these things very loosely.
Слева А есть, а справа А нет.
Because I didn't get finished. Then I wedge it with A. So A is some 0p minus 1 form. Okay? And also here there should be 2 pi r, because we have defined in an algebraic way already.
В левой части нету.
Correct.
Сейчас формы Стокса нету 2 пай да.
Ну, потому что вопрос, как определять границу. Что это формула Стокса надо делить на PI, когда мы границу определяем, когда вычислим. Потом я плюс. No, потому что так, like that we can do it over any field. And then, but if you want to have a complex of homology, we do not care about 2 pi.
А есть аналог вот цепного комплекса, или вот сингулярной гомологии есть с левой части, да, можно брать границу, потом еще границу. А тут есть аналог.
This is the same, the main subject of the talk. Precisely. Okay. So we have Stokes formula. This is so-called Cauchy formula, by the way, in complex analysis. And each time when I speak about this, I cannot resist on giving an example of Cauchy formula. So, for example, and this was in the class called PPU formula. And I remember how hard it was. PPU formula, which is one-dimensional case, which means that so the integral over c. So suppose f is some smooth function on c with complex support. And then let's apply this formula to the form f. To the form f. That, and for alpha, I will take form dz over z. And form f is 0, 0 form. Okay, then I will get d bar f dz over dz bar over z. And this should be 2 pi I. And then the integral over the residue of my form alpha. Alpha is dz over z, so this residue is just, the cycle will be just pointed with 1. And then I restrict my 0, 0 form to the point, so I get the value of f at 1. Yes, and this is a particular case of this holomorphic analog of Stokes formula. Okay. Okay, so now what about, as I have asked, what is a holomorphic analog of Черna-Sаймонsa theory? Let's translate these issues to the holomorphic in holomorphic terms by using this dictionary. So now holomorphic version of Черна-Саймонс theory, and this I think is due to Witten, yes?
Yes.
Okay, so let X be some compact complex variety, and as above it was a three-dimensional real variety, so let's suppose its complex dimension is 3. Then suppose let mu be holomorphic top form on X, and I suppose it is without zeros, so and poles. So this Calabi indeed, as you have. And so our space will be space A01. This will be the space of fields, the space of all 0, 1 forms. And given A, the functional S of A will be a similar thing. So there I have taken, is it still there? No, it's already not there, but I was taking D, I was weighting it with D of A, and then integrating using my orientation on M. Here I replace dA by d bar A. Yes, and so it is 0, 2 form. No, this is 0, 2 form, this is 0, 3 form. But I also have orientation. Then I wedge it with mu, and I take the integral over X. Again, it's a quadratic function on the space of fields. And now, given an oriented curve, what does mean oriented curve here? So suppose this is an algebraic or holomorphic curve, compact curve, and so I want orientation, yes? So alpha is some one form on C. Holomorphic. And as far as I understand here, it is not necessary to require that it doesn't have all zeros, so probably with zeros. So that the genus may be high. Then what we can do, so again, the functional that we can consider given by a curve is the integral, the thing I did there. So this integral, and so given 2 C1 alpha 1, C2 alpha 2, I can form a correlator of these two functionals. And so this will be again the integral in some clever way of e to the minus s of a times this product of the integrals. Okay, and a theorem which is due to Roslym. And this is how polar stuff appeared, as far as I understand. So the theorem tells the following. So here the theorem, we can do it in parallel actually. So here there was an assumption that both of them are trivial on first homology. We didn't yet define the complex that we will speak about, but already what does it mean that they're trivial on first homology? It means that both of them are boundary of something. So let's assume that they are polar holomorphic boundary of something. So assume there exist pairs Si beta I, where Si is a surface in X, beta I logarithmic two form, logarithmic on Si. Can I continue here?
What do you mean by surface?
surface in the sense that the complex dimension is 2. Here, Ci were curves, so complex. And then, so assume such that the residue of beta I from Si to Ci is precisely alpha I. So I mean that, better to say it like that, the top residue is Ci alpha I. So I mean that we have literally a surface Si. We have my Ci, the curve Ci is inside Si, and the form beta I has pole only along Ci, and its residue is alpha I. Okay. We have beta I. So suppose there are boundaries in that sense, in the holomorphic sense. If then this correlator written above is the so-called holomorphic linking number. C1 alpha 1, C2 alpha 2, which is by definition the following thing. So let's put here C1 alpha 1, say. We also have the curve C2 with alpha 2, which intersects somewhere the surface S1. It intersects somewhere the surface S1, right? In a well, everything is in general position, so we suppose it is infinitely many points. So on each of these points, what do we have? So I will sum. Now, usually in topology, what do? We want the intersection number of S1 with C2. What does it mean, intersection number? Of course, intersection number is not the number of intersections. It's the number of intersections with plus minus signs, according to what the orientation do. And so here, similarly, we should consider at each point what we do have. We have beta 2, which is beta 2 has poles. Beta 1, pardon. Beta 1 has poles only along C1. C1 is outside of C2, so this is point X. So here we have a holomorphic 2 form on the surface, beta 1. We also have, and this is tangent to the surface. We also have a holomorphic 1 form alpha 2, which is tangent to the curve C2, and they are perpendicular in a sense. And we should compare it with the orientation of the ambient space. We also have the 3 form mu. So we can do it something like that. We should take beta 1, which alpha 2 at point X. This will be a section of the determinant of the tangent space of one dimension, and divided by mu to the X. This will be some complex number. This is the linking number of 2 cycles like that, holomorphic cycles. And this is an interesting actually invariant. So, of course, it motivates to try to do some general theory about this. To define more, everything here I was saying something about, suppose that the form has pole only along this curve, otherwise it's not clear how to define. Of course, forms may have awful poles, and we also need to define some residue in this case. So all of this was just some rather intuitive thing based on some easiest cases. And now we would like to define some general framework for all this.
So you mean that you would like to extend the forms and the result will be independent of the extension?
You mean about this product?
Yeah, you need a form on...
Yeah, this is easy. This is because, well, you have the tangent space, you have, inside it you have canonically 2 subspaces, 1-dimensional subspace and 2-dimensional subspace that are orthogonal, that intersect only by 0. Then clearly the H power of the 3-dimensional space is the tensor product of the H power of 2-dimensional space by this 1-dimensional space. So yeah, you can extend, but of course it's linear algebra, it's well defined. It's all linear, so it is well defined, doesn't depend on the extension. Okay, but before maybe I go on, I wanted to give one example also told to me by Alexei, which I find very nice. It's due to Atya. It's due to Atya. An example of this linking number, which already appeared before, in some particular case. So one particular example. So you see, in a sense, here by this formula, by the right-hand side of the formula, it is defined some linking invariant, which defines on which depends on two cycles, algebraic cycles with forms on them. And of course, well, we can sometimes consider some schemes parameterizing this, and then we get some function on the square of the scheme without lossy where things intersect. Some homomorphic function, but algebraic in the algebraic framework. So we get some interesting functions on Hilbert schemes. Now let's consider the simplest example, which was found before by Etienne. As x, consider just the simplest thing, P3. Then by cycle Ci, so for each cycle, our cycles will be lines, linear embedded inside CP3. Consider lines. Then you would say that, of course, on lines we do not have holomorphic top forms, so it doesn't exist. But as I said, and it's again one more motivation, we could consider, we should consider forms with coefficients in some vector bundles. So what is the tangent? What is the canonical? What is canonical vector bundle on a line? It's O of minus 2. This O of minus 2 is restricted from O of minus 2, which lives on the whole embedded space. So let's consider everything with values in O of 2. So I can say that I have canonical, almost canonical, but it's okay, section of H0 of L, and here I take canonical class, and I trace it by OP3 of 2, restricted to L, because it is just O. Well, on O we also have many sections, but let's not look at this precisely for a moment. So then, given just a line, so then I see that given two lines on P3, I get some function, more precisely a section of some bundle. So I get a function on, so I get some homomorphic function phi on the Grassmannian in projection notations of lines in P3 times the Grassmannian of lines on P3 without divisor where T parameterizes pairs of intersecting lines. Ну, тут projection notations, поскольку есть три, а здесь
но тут никто не привык.
Вот, G24, so function 2C, some homomorphic function. And it has first order pole along T, by the way. And actually, one can calculate it in one particular case compared with something else, which is unknown. So we have so-called twistor space. We have vibration of CP3 over C4. Or for me, one can say that this is a quadric, and you have compact form of the quadric over reals. You have just Grassmannian over reals, which is, but you have also a sphere, yes, over reals as a quadric. And then so you have twistor space. So I will explain what you feel about this, but this gives you some canonical embedding of S4 inside the Grassmannian 2,4. And actually, the intersection of this divisor with S4 times S4 will be diagonal inside S4. And the claim is that the restriction of phi to S4 times S4 without diagonal is the green function. So function, well, you know, it's Laplacian, it's delta function of the diagonal. Here not Laplacian?
Not exactly.
You let me all these years.
Это оператор Лапласа минус 1/6 раскалярная кривизна.
Окей. Давай. Окей.
А можно повторить, что такое фи?
А фи это вот, so we have two lines. We have, I didn't also say that in all this business we need, we need cycles with top forms. So we want to have this holomorphic linking number. So we have two cycles indeed. We have two lines which do not intersect, and we have two forms, but two forms with various in line bundle. Also, I'm sorry, I didn't say an important thing. Also, we want to have a top orientation. Top orientation means we want to have some form, top form, on the ambient space with various in some also vector bundle. But you see here we take product of sections and divide by the third one. So both of them are forms with various in O of 2. So the product will be top form with various in O of 4. And here we have a very nice coincidence that so mu is the section on the core X, well CP3, of O of 4, which omega. And again, this cancels and it's just O. So this also gives one more motivation that it is important to do all that business with coefficients in some vector bundle, not just with forms. Okay. And now I pass to some more rigorous definitions in the algebraic geometry context. Yes, but before one last motivation, I'm sorry for having too much motivation. One last motivation that I should have said is the RAM theorem. So in this theorem that I will speak about, one want to have some theorem. So one of the main theorems on the left-hand side of the dictionary is the RAM theorem. Yes, which tells us what? So let me recall the RAM theorem that L over M is some local system. And let dimension of M, real dimension of M be D. M is the left-hand side of the dictionary, so it's a smooth manifold, compact manifold. And then the RAM theorem tells us that there is canonical isomorphism between, I'll write it like that, HD minus P of M. So we consider cohomology of M with coefficients in a local system. The local system is the tensor product of L by the orientation sheaf. It is not necessarily, it doesn't need to be orientable, so otherwise it is just trivial. And this is isomorphic to Borel-Moore homology of M with coefficients in L, where Borel-Moore homology are defined by locally finite chains. So we require that locally on each complex we should have finitely many chains in this complex. Borel-Moore homology. Okay, and so the left-hand side is translation in our right-hand side in the other sense is clear because so we replace M by X. So this corresponds to HD minus P, where X is some d-dimensional complex projective variety. Here we have some vector bundle with answered by omega X. I just translated with this dictionary. And so here,
probably it's good to mention that if M is compact, then on the right-hand side,
we have just usual, yes.
yes.
I'm sorry, yes. Yeah, I repeatedly said that M is compact, but it's not necessary here. I'm sorry, but I didn't try. Yeah, I'm sorry. So here also M it's not necessary that M is compact, I'm sorry. So here actually also X will not be necessarily projective. So here we have this, and the question is what is that, and what I will speak about. So now main result. Let me first give some definitions. So now, for me, it's a point that it's pure algebraic thing. So the theorem is proved in an algebraic context. I was permanently pronouncing the word holomorphic, but now everything will be algebraic just. And the proof is just algebraic. I don't know whether it happens or not to be true.
Everything can be defined
In a complex analytic.
In complex analytic.
Except that we don't have a proof with you. Yes, in the complex analytic case.
Can be given only in algebraic.
Yes. So let's go. But also, on the other hand side, it can be defined over any field, even over Q. Or it doesn't matter. So let K be some field. If you want, you can find. You can think it is, for example, a field of complex numbers. Of characteristic 0, it will be important because we will use here aналogom. Of characteristic 0, and let X be variety. Not necessarily smooth, nothing, just variety. But of course, I'm not assuming that variety is irreducible. Yeah, and let E over X be some vector bundle. Algebraic vector bundle. And denote by XP the set of all subvarieties inside X, subvarieties, closed subvarieties, algebraic subvarieties, irreducible, of dimension equals P. Actually, for those who know, we'll do something of Gershon complex type. Now, I want to say what are this will be Z as it was above. Now, for each Z, I want to put some orientation in the above sense. I want to define tributes in that. So orientation, as you remember, it were some polar top forms, some top forms with logarithmic singularities or with various in a vector bundle. But I only define what are logarithmic singularities when we have a smooth variety and a smooth divisor on it. And now it's time to define what are them in general. And so it's natural to consider things like that. So definition, also notation. So let denote by K. So fix for now fix Z or dimension P, and put K to be the field of rational functions on Z. Rational functions on Z. If you are in a purely complex context, then and if everything is projective, then you can just consider the field of meromorphic functions. Put this and denote by omega sub k the set of all rational, or if you want meromorphic, with very awful poles. Rational top differential forms on Z. So they have some awful poles along Z. And denote by EK all rational sections. Sections of E restricted to Z. Z is reducible. Now the definition. So I want inside the tensor product of omega k. So omega k is one-dimensional vector space over k. Ek is rank E dimensional vector space over k. And inside the tensor product, so inside all rational top forms with coefficients in E, I want to distinguish some logarithmic forms. How do I do? So alpha inside omega k tensor Ek is called polar if the following holds. There exists proper birational map. I will please comment what this is. Proper, and it's not to be proper birational map. Though the varieties may not be proper, but I require that the morphism to be proper. F from some V to Z such that V is smooth. There exists some W on V, which is a simple normal crossing device. I will comment on these notions. And there is alpha V, which is a section on V of omega V, tensor F alpha star E restricted to Z, and with poles above W, such that F alpha star alpha is alpha V.
You could have said just that the pullback is logarithmic.
Yes, the pullback is logarithmic.
The pullback to V, yes?
Pullback to V. So first of all, what does it mean bidirectional? It means that you have some open, Zariski open subsets here, on which F is an isomorphism, which means that you have your variety Z, but you have your singularities only could dimension at least one. So you modify some varieties. You glue something instead of your subvarieties to your V, to your Z, and you get some nice variety V. This is a typical example of the resolution of singularities. Yes, that's why we assumed it is important that the characteristic is zero, because of characteristic zero. By the way, a very strong theorem by Hiromaka tells that for any variety Z, there exists a map like that with this property, that it is bidirectional proper and V is smooth. And proper means that fibers are compact. Because of course, easily there is, if you broke this condition,
But
then
V has to be of the same dimension, right?
it's bidirectional, yes, and Z is reducible. Because if you drop this condition, then it's nothing, because you can just consider an open embedding of smooth loci inside Z, and this is nothing about it. So it really should map to the whole. In particular, any proper map must be surjective. It's a theorem of algebraic geometry, so in particular it means that it's surjective. So really, if you had some problems somewhere on Z, you must solve all these singularities, you must solve all these problems by taking V. Okay, then, so my alpha had some awful singularities on Z, but I require that after some nice pullback, it starts having some nice singularities. So a typical example of this, one example, is just the example that was above. Then you have a smooth variety V, you have smooth divisor W, and you have a form of first order polar along W. This is easy. But of course this is not enough, because for example you want to take sums of forms like that. For example, your form dx over x, plus dy over I, or dx over x wedge dy over y. It is not like that, but dx over x, its singularities, and plus wedge dy over y, its singularities is a cross. And cross is okay. And this is the best you can get, and this is not. So simple normal cross divisor, it's a very typical notion of algebraic geometry, which means some generalization of just a smooth divisor, and almost all theorems that you have about smooth divisor hold for simple normal crossing divisors. So simple normal crossing divisor just means that W is a collection of Wi and Wi inside V. Let's say global simple normal crossing. You can always achieve it. It's rigorously it's called global. One is a union of smooth divisors. So we have some smooth divisors, and the point is that they intersect transversely. So at each point, the new divisor gives you a non-trivial new condition on the tangent space, so to say. So for example, on a surface, you cannot have a Hedgehog like that, because the third of them doesn't give any new condition on the tangent space, yes? So you want that, in other words, you want that all intersection have a dimension equal to the number of components you have considered. So again, on d-dimensional variety, you have at most d divisors that can meet in one point. But they can be two of them, for example. And it is easy to define what does it mean that your form is logarithmic along it. Well, I even didn't use here the notion logarithmic. I just said that it has this is notation from algebraic geometry means that so this is a vector bundle well defined on the whole V, and are required to have first order pole along W. Okay. Some questions? This is the main notion here. And denote like that O Z of E, the set of O alpha, beta polar. So an easy remark is that this is subset, but it is actually a subgroup. So we have two of them. You can take the sum and it will be again like that. This is just because so we have alpha and beta like that, for example, just to feel a bit. So alpha regularizes to some V alpha, beta regularizes on some alpha on some V, beta on some V prime. But you can take a common desingularization. It's a general statement from algebraic geometry. If you have two V and V prime, then you have a common V double prime that maps to each of them. And then you do pullback of all things. You can also, by Hironaka, you can also, so Hironaka theorem is even stronger than just desingularization. It tells you that if you have variety Z with some awful singularities, and you have some variety B, you can always find V, such that the preimage of V will be a logarithmic, will be a simple normal crossing divisor. So, for example, you do it like that, well, I think I explained. So even if you want to sum, even if you sum two forms, one has poles along here and another has poles along here, for example. So formally there are some here on this surface. It doesn't have a singularity of that sort, but after nice blow up, it does. Okay, it's a K-vector space. Yeah, we can also multiply by scalar. It's clear K-vector space. And the point is that out of this you can cook up a complex. So the constructions that given B inside Z, so B is, let B be of dimension less by 1. So you have your big X, you have Z inside Z, you have per dimension one thing. And alpha, which is polar on Z, we have the residue from Z to B of alpha, we define, which is a polar element on B. So they nicely form a complex. You start getting differential. Why? Because well, you want to define a residue to B. I defined how to do it if you have some smooth divisor W on smooth V. And but if well, you can desingularize everything and get that your B will be in good. Your preimage of B will be in good position with respect to this W. It will be either a component of W or it will be transverse to W. And if it is a component of W, then up here you can define a residue as it's did. And then you push down from this component which maps surjectively and properly, so you can take a push forward back to B. So the residue is defined. And so well, in the simplest way, when you have just smooth W, when you have just smooth B inside Z, then and alpha is just some section of Z with various omega Z of B, then this residue from Z B of alpha is as usual. The coefficient by dt over Z restricted to B. And the power of Hironaka theorem is that you can do all of this after you desingularize stuff. And then push down. Okay? And now, out of this, we can form a complex, which is called a polar complex. Now put pole P of xe with the direct sum over all Z of dimension P of these groups, vector space, pole Z. P. So an element here is just formal sum of pairs Z alpha Z, where alpha Z is from pole Z. Final sums. I get a vector space like that, and then I can define a differential from pole P of xp to pole P minus 1 of xe. And this is just the sum of all residues over all P inside Z of residues from Z to B. So given the chain here, I want to get a chain here. I for each member here, term here, Z alpha, I consider all possible residues defined as above to all be living inside Z. And the point is that actually for a fixed alpha, you have only finitely many P's such that the residue doesn't vanish. It's clear because after this synchronization, you have only finitely many divisors along which your form alpha has singularities. Okay. And a claim.
Say find the many components of the device, right?
Yes, yes. The claim is that d squared equals 0. And just to have a feeling how it works is that, for example, if you have for Z, if you have some plane, and then your form alpha is dx over x, where is dy over I, then what is d of Z alpha? D of Z alpha. So I test all curves on the plane, and I want to take residue to all curves. If my curve is neither vertical axis or horizontal axis, then the residue vanishes. It is regular at the generic point of the curve plane and the name is just regular. So I have only two, so we'll call this L1, L2. So I have L1 with, say, dx over x, and actually minus L2 dy over y. And then if I take the residue again, so where does this, see here I have a fine line and I have form dx over x. It has all at the origin, and the residue at the origin is 1. So it will be origin, point origin, and some number which is 1, and this gives you minus 1, which means so d squared equals 0.
Может еще вопрос, я не помню про определение дифференциала. То есть
Да.
мы взяли разрешительные особенности, взяли там какой-то дивизор, взяли у него вот этот вычет, а потом отображение из дивизоров наш x, оно не обязательно же рациональное. Там может быть какая-то конечная степень, например.
Да, это надо учитывать. Но есть прямой собственное. Если есть прямой образ, если, собственно, есть морфизм,
да, всегда
одинаковой степени, одинаковой размерности многообразия, то есть прямой образ на рациональных формах.
хорошо.
След на рациональных формах есть. Но то, что рациональная форма сверху, это pullback рациональной формы снизу. А всегда это след. Вот. Хорошо. Okay. So now we get a complex. And now the main theorem. This is what we tells that if X is smooth quasi-projective variety, quasi-projective, well, it means that open and projective. Then d-dimensional variety. Then there is natural isomorphism between hd minus p, so the left-hand side which was omega tensor b equals omega, with p homology for this polar complex. This is the theorem. So in algebraic geometry, if you have some vector bundle on the right, you have cohomology, coherent cohomology. And they can be actually calculated by this very explicit complex. And this is translation of the round theorem by the dictionary, by our dictionary. Well, this was of course translated by Haysen and Roslym, but then it was proved by Alexey and Haysen and Boris in the complex case for, I guess, for projective varieties, yes?
For projective.
And what is more important with trivial coefficients?
The work of three authors, also Richard Thomas.
Yes, I'm sorry, with Richard Thomas again also was the co-author.
Haysen
And Roslym.
and Roslym.
Yes. And this was with trivial coefficients and by some complex, rather complex analytic methods, yes?
No,
No, so-
the method, the methods were complex analytic, but the context was projective money.
Yes. And this is with okay. So for the rest, maybe I will comment a bit about some ways. So we have 15 minutes, yes. So I will first maybe a little bit comment about proof, and then maybe if time remains, say something about applications. So the idea of the proof is the following. So how do you prove it in topology? So what I like about the proof is that it is really a translation of topological proof. So what you do in topology is you just show that you out of the complex that calculates Borel homology, you do some complex of Flaby shifts on manifold M. You do some complex of Flaby shifts, and then you just show that this complex is acyclic and its H0 sheaf. H0 is just your sheaf F. And the fact that it's locally cyclic is sort of Poincare, which uses something you can do locally on smooth varieties. You can, for example, that any cycle can be locally a residue of something. You do something like a color neighborhood or tubular neighborhood, something like that. And the idea was to do the same in algebraic geometry context. And so it's absolutely trivial how to do a complex of Flaby shifts out of this complex. Just its section over U is pole of U, nothing else. This is clear, but the idea is what is its H0 and why is it locally cyclic? So why is it true that locally, Zariski locally, each cycle is boundary or something, which it turns out to be true. So the theorem is somehow divided into two steps. One is to show that, so part one, one is to show that cohomology D of pole, one is to say that H0 cohomology of the sheaf of complex of sheaves. And actually, it's not so hard to describe what is this thing, but you might expect it should be omega tensor E, but it would be really strange because there's nothing coherent about this. These are not sheaves of all modules even. You cannot multiply it by functions. So the kernel cannot be like that. And it's a second funny thing. So you can. It is the following sheaf. It is the following sheaf. It's the sheaf omega tensor E, and then you do pole, where given any vector bundle E or constant sheaf, locally free sheaf F, define F pole as follows. It's some subsheaf inside F, defined as a risky subsheaf, defined as follows. F pole of U is H0 of X tilde, I will write down. So let X tilde be some proper biaxial morphism. Here you have X without U, and here I want it to be globally normal crossing divisor. Okay, so I have some open subset in my variety. It has some awful boundary, and I want to singularize such that the boundary becomes globally normal crossing divisor. And then I consider here what is called pi upper shriek, of f, which is nothing but the following. It comes from Buddhistic duality. It's omega x tilde tensor pi upper star of omega x minus 1 tensor f. Of course, with poles along t, tilde, along t. This d.
First order poles.
First of the pole. So it's not an O submodel, it's some subsheaf of abelian groups. You can say that this is subsheaf of sections that have first order poles along the boundary.
That was F once again.
F is some vector bundle, or locally constant sheaf, locally free sheaf. So you can define the subsheaf of sections that have only first order pole on the boundary in that way. And the claim is that actually, so it's H naught of this polar complex with these sheaves. And theorem 1 tells that cohomology of XF pole are isomorphic to cohomology of the whole sheaf. Always.
And what is called with X?
Canonical sheaf.
But X is not smooth.
X was smooth in the theorem.
X is smooth.
In the theorem, X was smooth. X is smooth. But quite projective.
Actually, in the round theorem, we also need smoothness. In this classical.
Yes, you're absolutely right. In the round theorem, we also, if you don't go to session. Okay, and now theorem 2 tells that higher order sheaves of cohomology vanish, which means that, so this is Poincaré lemma. Which says that locally each cocycle is a coboundary. Or let us say cycle is a boundary. And the idea how to do it, which I like, is the following, that so how to do, would it be, you also want to do something like you do in topology. In topology you just want to have some tubular neighborhood of your cycle and then represent it as a boundary of, and suppose, so idea is the following. Suppose you have some variety x and you have some variety, z, and we have, suppose we had some tubular neighborhood. So we had some variety t inside x, such that there existed also a projection p back to z. So this is ip is identity on z, and also so we have some point x, and here we had some form alpha, and we want it to be locally. We want this morphism to be smooth at the point, so we want that z to be locally t equals 0 on t.
Maybe it's may cause confusion. We call it tubular neighborhood.
It's color.
Tubular is, I mean, of full dimension.
Yeah, so it's color.
This
Color.
is of
Yep.
one dimension
Yes, certainly.
greater.
Maybe it's color neighborhood.
Something like this, yes.
But it-
It's not a neighbor.
Not in neighborhood. It's not a neighborhood. Yes, not a neighborhood. Ну ладно, in neighborhood. Окей, but some. А как это лучше сказать? Thickening. Да, thickening. Okay, thickening. So, and if it exists like that, then you can just repeat more or less the same as the topology. Then you can say that your cycle z alpha is just a boundary of what? Of t beta, where beta is what? Beta is dt vht, dt over t, which p apostolic alpha. So if your alpha, if you want to use the condition that d of the alpha vanishes, so suppose for simplicity that alpha is just regular, it doesn't have any pole, then of course the full residue of this guy will have only residue along z, and its residue will be alpha. Yes, but in general, in algebraic geometry, of course, it doesn't exist t like that. Zariski locally, but it exists Nisnevich locally. And here we use Nisnevich topology, but one can more precisely, actually, Nisnevich topology was invented before by Quillen when he was proving Gershwin conjecture. So it's very similar to Gershwin complexes in algebraic theory, and there is a very powerful method so-called Quillen's tree, and it allows to construct kind of T like that. Though they don't exist previously, but a way to overcome it. And actually, it's the same, but not in Zariski, but in Nisnevich topology. Okay, and some last comments about how it's related to some other stuff. So, one funny thing is that it, for example, it allows us to define classes of cycles. Many decades ago, there was a problem to define cycles of classes in the random homology, or in HI or omega I. And so it's very visible by this complex. I wanted to present it. So cycle class. So suppose we have some variety here of dimension B. The X is smooth. So I want to define a class of X in HP, or so let's suppose now that it is codimension, okay, of X omega P. And out of this complex, it's very easy to do. How to do? So I consider the singularization of this cycle. The cycle may be singular. I consider singularization. And then I want to say that I get I have kind of Gauss map. My differential. Differential gives me a map. So one has canonical element alpha z, where in H naught in H naught of V, so I have a map from I have d pi well, yeah, let's denote this by f. I have df from the tangent space of V to the alpha star of tangent space of X. Now I can pass to wedge forms. I can take the determinant here and take the corresponding wedge from wedge power here. So I get a map from where? From d minus p tv to lambda d minus p or fullback lambda d minus p tx. This is the same as H naught of V omega V. Tensor what? Tensor this thing. Yes. So I get a canonical cycle. So we get canonical cycle Z alpha, where in pole X with value here f of a star d minus ptx. Yes? Oh, I erased my theorem, but now the theorem tells us that d minus pth homology, dimension is d minus p. D minus pth homology of this complex isomorphic to pth homology of X with coefficients in this sheaf without that. Tensor omega X. Now this is canonical isomorphic to omega P. Okay, and last remark that also it has relations to Cousin complex. Generally, for example, in Harshon's book Residues and Dualities, it's very good about what is Cousin complex, and one has sort of Cousin complex for any locally free sheaf, for any vector bundle on a smooth variety. This Cousin complex, you may say that the polar complex is first order part of the Cousin complex. So for example, on a curve, your Cousin complex looks as follows. You consider all rational functions, say forms or rational forms on the curve, and then you take the direct sum over quotients over rational forms over locally regular forms. This is cosine complex, and there is a generalization of it for any locally free sheaf on any smooth variety, and it calculates cohomology by general nonsense. Actually, it calculates cohomology of the vector bundle. And here we kind of consider only these polar elements with first order pole. Here, guys of first order pole is just the sum over all fields of residues, and this is residues. And this is the polar complex associated to the canonical sheaf on the curve. So one can say that our complex is a first order pole, much smaller subcomplex inside the cosine complex, and it's still quite isomorphic to it. This is the theory. And also, well, last maybe remark that for me it was also interesting because there is some other resolution which is called adelic resolution for constructed by Billingstonian function for any coherent sheaf on any scheme. In particular, for this one has another resolution called adelic one, and it is defined over any field. So over C there is Darboux resolution. And polar complex is something in between both of them, and it gives you some explicit way to construct quasi-isomorphisms between these two complexes over C. So there was actually a question long ago by Pasha how to construct an explicit quasi-isomorphism between adelic resolution and Darboux resolution, because there are many analogies between them when we have spherical varieties over C, and polar complex allows to do it explicitly. You pass through polar complex somehow. So.
And the maps go in which direction?
No, it's a chain of quasi-isomorphisms. It's like that. But it's not something abstract, yes, it's a chain of explicit quasi-isomorphisms.
It's not that polar maps multiple.
No, it cannot do it. Okay, thank you very much.